What do you suggest? Will we start with the next presentation by Chris de Jong? Chris de Jong is a well-known person to many of us. He's from TNO, the Netherlands Organization of Applied Scientific Research. Also affiliated with the Technical University in Delft, if I'm right, Chris, still. And you will inform us about modeling aspects of the JOMOPANS project. So the floor is yours.
Good morning, thanks. Well, welcome all at this meeting. I'm happy to kick off the technical content presentation with the Soundscape modeling work package, because that's the work package where we produce the maps that have been mentioned and shown by Niels. And I'll briefly try to tell you a bit more about the background of these maps. So if the point of a map is it's a way to monitor the sound in the seas, and it's because this underwater sound pressure that we are looking at, it varies with location, it varies with time, it varies with frequency, and it's generated by multiple sources. And by sticking a single hydrophone in the water, you get a local impression of what's happening at that moment in time at that location. By modeling, you can get a much broader view on what's going on. So the maps that we've modeled are two-dimensional representations of the soundscape in the North Sea, actually. And then, of course, we have to do something with the other dimensions, the depth, the time period, the frequency range, and we made definitions and try to capture those in variations of the maps. The advantage of modeling is that you can assess individual contributions of different sources, and you can execute scenario studies in a later stage. So that's why we focused for a lot on maps, and we use the measurements to check on the uncertainties in what we are predicting. Making maps for the North Sea is quite a complex process, because you have to use to find the input on what to model, and then go through a process of generating the correct parameters, finding the models, and then in the end producing the soundscape maps that you want. Well, we focused on the North Sea area. We look to temporal percentiles of the sound pressure, so how often does a certain level occur during the month. We look to a depth average. We cover a broad range of frequencies, which include the range where the shipping and wind noise are, which we consider the most important sources of noise in the North Sea, can be modeled. The inputs we collect from publicly available data sources. And of course, if we want to model shipping and wind, I see that the resolution is not great in the presentation, but the figure to the left is the AIS, the information that Niels already referred to, that gives information on where the ships are. And these are from satellites and from ships, and we try to get a coherent picture of what's going on, which involves quite some from processing actually of the available data. Then we characterize the environment in terms of the sediment properties. The grain size of the seafloor is an important parameter for the acoustic propagation. We look to the bathymetry, water depth is important. And of course, we look to the wind because that both generates noise by wave breaking, and it affects sound propagation. So that's both effects are in there. And we use these public databases as input. And then we go to the modeling stage. Well, modeling means that for each of these sources, you need to know how much sound they generate. And for ships, that was not straightforward to be able to quantify how much ships are making. There are some models being used in the past based mainly on work done after the Second World War by navies to know something more about how to detect each other. Not all of these are directly clear where the data come from, and to get a better view on what ships actually are producing, the noise they are producing, we sought collaboration with the ECHO program in Canada, where they had a very nice study and possibilities to measure individual ships in large quantities. So we have a database. They have a database of ships and their source levels, the sound they generate, for the various ship types with ship type, ship length, and ship speed as parameters. And we together with the ESCO, we came up with an updated model for the ships in the North Sea, which was published in a paper early this year. That's used as input for the models that we are making. Well, then sound propagation has to be modeled, and many different models are available. Not all models are as suitable for the typical shallow water environment of the North Sea. So what we did, together with the Work Package 4 partners, MPL, FOI, Quiet Oceans, and JESCO, we looked to the different models that are available. We came up with a set of propagation model benchmarks so that we could test various models against each other. And in the end, we provide these benchmarks and the solutions also as input for future modeling efforts, so that people can test their own models in the future against benchmarked solutions. So that offers the opportunity to make sound maps with a benchmarked and verified model. The models themselves are not the main source of uncertainty in the maps we are generating. We've seen from these benchmarks that when properly implemented, these models can be quite equal the results. Then, of course, for the large-scale modeling, you have to make various assumptions to be able to quantify the sound over this large area for the large amount of time that we have. So we had to make some assumptions for the North Sea. The final maps are made by the model implementation generated by TNO. We ignore the sound spate profiles because these are not the dominant source of uncertainty in the shallow water environment that we're looking at. For the ship noise, we chose to ignore surface waves so that we have a constant environment in our models, and we pre-compute the propagation loss between all the sources and the receivers so that we can create dynamic pictures of what's going on without having to repeat the calculations on propagation loss. Well, for making these maps in the end, the figure up to the right gives an idea about the total amount of time that we used for it. It's not very clear, but in total, I think we spent 146 days of calculation time to generate the dynamic sound maps of the North Sea that we, for 1 year, that we produce in JOMOPANS. And the whole process on how these maps are made, and also guidelines, lessons learned of what we had, are described in a guidelines report for future use. Well, that leads us to led us to the maps, and of course it's nice to see that these are dynamic. So with another click, I can demonstrate that these are dynamic. For every 10 minutes of we have a snapshot of ships that are passing and sound they're producing. For every 10 minutes of the year, we've made these maps. Well, that's very nice to look at, but doesn't give much direct information. So we collected these in statistical maps in various representations. And as an example, we show here the annual median sound pressure in the seas in various frequency bands, one below 200 Hertz, one between 200 Hertz and 2 kilohertz, and one above 2 kilohertz. And this demonstrates clearly that there's noise at the areas where there's lots of ships. So shipping noise is an important source in our models, but also in real life. And it's a low frequency phenomenon, more or less. If you go to the higher frequencies, it extends not as far as it as in the low frequency range. Well, as Niels already said, we produced a lot of maps, in total 1,248 that can be visualized. They are soundscapes in the sea. They give individual contributions of different ship types for different frequency bands and for the individual months of 2009. And then also measures where the ship noise is compared with wind noise to have an idea of where the ship noise exceeds over the wind noise. And these will be addressed later in later presentations. So in conclusion, with these new maps, we have a clear insight in the relevance of shipping noise for the North Sea soundscape, actually. So we want a global overview without seams, which we didn't have before. As also indicated, this is a very nice first overview of the sound of ships and wind. Of course, there's more going on the seas, and there are also issues to be solved to be able to quantify how certain we are about these maps. Some of that was addressed in the JOMOPANS project, but there are still remaining open issues. And one of the issues is, of course, that we need to add in sources that are not there, both ships that are not covered by AIS as the sources that we haven't covered in our modeling, like operational wind farms and oil and gas related activities. So that, and we have a limited number of locations where we could do the validations. And of course, at the other locations, it's much more uncertain to quantify how well we know what the sound levels are there. And an important next step to be made is to extend this whole mapping ability from looking just to sound pressure, also looking to particle motion, sound particle motion, to which many of the species in the seas are more sensitive than to sound pressure, actually. And that's an activity that's taken up in the Saturn program that has just started, a large European Horizon 2020 program. The outcome, the mapping ability that we've created has already led to a first application outside JOMOPANS, and this we presented at a seminar at the end of March in a study for the Belgian government. We looked at the scenario study where we tried to find out what would be the effect of setting a speed limit to the ships at the North Sea, and demonstrated that if you limit these ships to a maximum speed of 75% of their design speed, then you can get a reduction of the shipping noise on the North Sea. It's not very large reduction, but it's a nice example of what this study can give you. Well, with that, I hope I stayed in the time frame, and I thank you very much for your attention.
Thank you very much, Chris. You did very well on the time, exactly 10 minutes. So thank you very much. And I look at Barry to see whether there are any questions already through the chat.
We have two questions, one from Jochem and one from Andreas. Jochem's question is whether the 10 minutes maps are available for each frequency band. And the question by Andreas is, the time resolution of the shipping noise is 1 second. What is the time resolution of the wind noise?
Did you get those, Chris?
Yes, I got both questions. To answer Johan, yes, we made these maps for all frequencies for all snapshots. So it's the 34 frequency bands. We calculated the maps for at the center frequencies of the 1/3 octave bands, and we did that for every 10 minutes of the year, actually, of 2019. In the extension that was mentioned, we hope to be able to make the similar series of maps for 2020, which might show some of the effects of the changes in shipping over this last year, perhaps related to COVID. The other question is about time about the time resolution, and that's indeed an important one. For the measurements, we've identified a 1 second interval as a relevant interval for marine life. So we are looking to the changes of the sound, the statistics of the sound as it changes over every second. We cannot calculate the whole year every second. So in a good approximation of the monthly statistics, we made calculations for every 10 minutes. We have the AIS data available at that time resolution. We don't have the wind data at that time resolution. We have hourly wind maps, and what we did is for our calculations, we interpolated those hourly wind maps to a 10 minutes time step. Is that answering your question?
I think it does. I don't know if there's time for 2 more questions.
Yes, I think so.
Yes?
Yep.
Okay, there are 2 questions about the Dogger Bank. Sven is asking, I would have expected to see heavy fishing pressure on Dogger Bank. Don't we see it because trawlers are not concentrated on lanes? And the next question is, why is the Dogger's Bank quieter for the lowest frequency band than for the mid-frequency band?
That I'm happy with these questions because they. One of the things is the Dogger bank is more shallow than the surrounding waters, and one of the consequences of shallow water is that the lower frequencies don't propagate as well. So the most likely explanation for the lower levels in the lowest frequency bands on the Dogger bank is the fact that it's more shallow water. So that should be real. That's. An issue with the Dogger bank is that it is outside the shipping ranges. It's for the maps we use data from AIS, both from satellites and from land-based stations. All were collected. For a number of countries, we managed to supplement that data with VMS data, VMS recordings, and many fishing vessels are present in the VMS, but not always in the AIS. Unfortunately, we only got VMS data for this project from the European countries. Let me state it like this: or from Germany, from Denmark, from Norway, I believe, but we didn't get them from the UK. So a large area of the Dogger bank where we don't have the VMS data. So it's possible that some of these vessels that are mentioned in the question are not available in the AIS data. We don't have measurement stations there, so there's no way to validate that at this moment. It is an area remote from the coast, from the shore, and so we are more relying on AIS data, so on AIS data for satellites there, and then coverage is an issue. So AIS coverage for the North Sea is one of the things that we should look closer into for future efforts.
Cool, thank you very much, Christ. I have a small follow-up on that. You addressed validation. You have the AIS-based data and modeling. What is the opportunity now with the real-time recordings that we have to do that validation? Do you have any suggestion about how that can be approached?
I believe that my colleague Ross Petland will tell us a lot more about that, because JOMOPANS had the work package 6 as especially addressing the validation of the data, using the measurements to validate the maps. Yeah.
Excellent. Then we will wait for Rosalind. Okay, thank you very much, Christ.